I start recording. Welcome to the seminar or webinar number 10 of our series of webinars for the 6456 edition. And we have today 3 topics and 3 presenters. You heard already Gundula, which you know very well. She will talk to you about low power modes. And Rene Saupe will join and is joining already. He's talking about multi-compartment washing machines. And I take over the first topic, the intermittently recurring function. Before I come to this point, I show you here a little CV of these 3 presenters. You know most of them already, and they will introduce themselves as well. And going on, here is a little time plan, and we will have questions and answer sessions after each section. But if you have questions in between, don't mind to interrupt the presenter and ask it if it's an urgent need to get it answered. Yeah, so the first topic is a little bit to talk about what we did not cover in the webinars number 1 to 9. So you have seen this chart, which is in the 6th edition, giving an overview. And you see we have quite a lot of different performance measures, so which define the washing machine performance. And we have talked about most of those topics already. So the cleaning performance, a new evaluation scheme was topic in number 4 webinar. The introducing cleaning test for cotton was in webinar 2. The cold water cleaning in webinar 3. The wool cleaning in webinar 6. Gentleness of action webinar 5. Wool shrink is in 6, LAS rinsing in webinar number 8, and alkalinity as well. And wash low temperature was touched in webinar number 4. Energy measurement, water consumption measurement were all touched in webinar number 4. So you see there is not much left. One big point is missing. These are the low power mode consumption, which is the topic for today. Then we have at the bottom right, we have the water extraction performance, but there has nothing changed. So this is nothing new. And then we have on the left, you see some annexes mentioned, which are new or partly new in the new edition, which are these intermittently recurring functions, multi-compartment washing machines, and low power modes. So this is the topic of this webinar number 10, where only partly of this will be tested in the round-robin test. But we think it's worth for you to explain what is behind those annexes and how you may have to deal with them when you have to measure certain functions. And the first function I want to talk to you about is the intermittently recurring function. It's a strange name, at least I think for most of you, as it was not used before in the standard. What is it? These are functions which are intermittently recurring. So they are not constant functions which always happen during a program execution, but they happen time by time. And if these functions are happening, then the program execution is changed. And this can affect the water consumption, energy consumption, program duration, or whatsoever. Yeah. So we have those functions which are really, let's say, more or less spontaneous happening during a program execution. when we recognize such kind of a function, the question is, what then is the correct value for a washing machine which we are measuring in the laboratory? So if you are a independent laboratory and you get one machine delivered by a competitor or by market surveillance, and you are asked to measure it, you come to the question, oh, what is the correct value if you have those intermittently recurring functions happening? The first option is to say, okay, I don't take care of that. I take just what I'm measuring. And so I will measure 5 cycles, for example, and I take those values. But if these functions are affecting energy, water consumption, then you will have 5 very different values, which are not repeating the same program, but they are measuring different programs. So we don't have the requirement for calculating the repeatability like the standard deviation, that we are repeating the same experiment n times, 5 times. So this is not fulfilled. And therefore, when we just take the values and calculate the standard deviation, we will see that we have a high uncertainty in the value. And this means it's hard to use these values to compare the data of one machine with another machine measured in another lab, or just with different repetitions of your test series. Yeah. So this is, let's say, not a good option just to say we take what we are measuring and this it is. Another possibility is that one is switching off all those intermittently recurring functions, if that is possible. But this would result that we are measuring something like a minimum consumption, which may be not realistic. So not representing that what the consumer would get when using this machine. And there may be also influences coming on the performance measurement, because those intermittently recurring functions may be necessary to bring the machine in a status that it is delivering the performance it should deliver. So also this is not a good solution. And the third one is to measure many cycles, not only 5, but perhaps 10 or 20, to understand what is behind those intermittently recurring functions, and then to see that there may be 2 or 3 different stati of the functioning of the machine, and then you can try to understand what is behind it. Though this may mean that you have to do a lot of tests, and you are not sure what you get as an output. So this is just very theoretical. Let me give you an example. I have made up here an artificial example, and I just look on the water measured on one machine in lab number 5, in 5 cycles. In lab number 1, 5 cycles. So you see, there we have values. It starts with 70 liters, goes down to 50 liters, and then goes up to 75 liters. And this is what we see when we take these 5 samples. And the average here is something like 60 liters. When we take the same machine and give it to a second laboratory, or we measure it again in the first laboratory, we may end up with these data here. So we start with 50 liters, then we have 70 liters, 55, 50, 50. The average would be 55, so 5 liters lower as in lab 1 or measurement number 1. So this is what could happen. And this is the effect of this intermittently recurring functions. And yeah, the difference is more than 10%, which is out of that what we expect to be able to deliver for a water measurement, for example. But these are only artificial examples. Let me explain what could cause such a unstable behavior of the machine. Actually, when we just see the data, we are not sure what is it. Is it an unstable behavior of the machine, or are the test conditions not stable so that the machine is switching from one cycle to another? For example, if some fuzzy logic is active, some load detection is active, then it can be also the test conditions which are influencing and which are giving these unstable results. So it's not per se easy to understand such a behavior when you measure it in a laboratory and you don't know much about the machine itself, how it is working. So how can this happen? I have, let's say, thought of two intermittently recurring functions, which we have already today in washing machines. The one is there are washing machines which have a water softening device in. This takes out the calcium, magnesium from the water, from the tap water, and delivers soft water for the washing, which is beneficial for the washing, which is very good. But this softening of the water happens by using a resin, and the capacity of the resin is limited, so you can take out a certain amount of calcium and magnesium ions. If the resin is at the end of its capacity, it needs to be regenerated, and for this you need to run a regeneration cycle, which is normally done by flushing it with sodium chloride solution, so salt solution, and by that it is regenerated. But you also then need to flush out this salt solution, so from the resin, so that it can continue to work as it should do. And this needs some amount of water. Can be 2 liters, can be 5 liters, but this only will happen when the capacity of the resin is at the end. And therefore, it's not happening at each cycle. It's happening after a certain amount of water intake, or however it is programmed in the program of the machine. So this is one of the intermittently recurring functions which we have already today. And the second one is that we have water tanks in washing machines, where the last rinsing water is stored for reuse in the next cycle. This is good to save water and to save also some energy. But we are storing in those machines, water is stored for a certain time in a tank, and you should not keep this water for a too long time, because then molds would grow in this water, and this would not be good for the next washing cycles. So those machines, at least as I know them, they all have some kind of a time control in, where they are registering how long is the water staying in this water tank. So what is the time between the last cycle and when is the next cycle running? And in those machines, they say that after, let's say, 48 hours or 72 hours, the water is pumped out again to avoid that the molds are growing in this tank. So these are just two functions which we have already. And we have to think about how to measure really the correct value for all those performance parameters, water, energy consumption, duration. What is the correct value? And this correct value, yeah, when you look on these examples, it's not easy to say, because it depends, for example, on the water hardness region you are living in, or how long it takes for you to go from the one to the next cycle. If it's a weekend in between, then it's easy to extend or to come to this 48-hour limit or even 72-hour limit. So it really depends on how the consumer is using this machine, and this will influence what one could see as a correct value. Yeah, so what is the problem is that we want to measure what is the influence coming from those intermittently recurring functions. And we want to be able to say, okay, this is the basic consumption of a machine. And when the intermittently recurring function number 1 is triggered, then it will consume so much additional energy or water. And when the intermittently recurring function 2 is triggered, it will cost so much, so that we can really have a clear view on what is the machine doing, and can take this information also to come to a correct information to the consumer when he, let's say, wants to know what is the consumption values I have to expect from such a machine. Yeah, so this is a definition from the 6th edition. So a function that occurs during or after some, but not all cycles of a specific program, and which alters water consumption, energy consumption, or program duration for the cycle. Yeah, so we need to find a way how we can really come up with some values which are statistically significant, so that we can really say these are the values with a good accuracy, and we can use these values for coming up with some right consumer information. So what was the approach which we did, which we took to come to a measurement of this intermittently recurring functions? This principle is defined in Annex T of the standard. It's not so easy to read. Don't be confused. In principle, it's simple. And what I'd really try to do is to give you some introduction to that. And this will help you to understand that it is simple. So what we want to measure is, on the first point, is to measure the basic value of the cycle without an intermittently recurring function activated, which is, let's say, so the minimum consumption such a machine has. And we want to measure what is the value with the IRFs, so that we see what is the difference. And we want to verify that this difference is, let's say, clear, significant, which is on one side confirming that what is given by the manufacturer in his information, in his instruction manual, so that the consumer, when reading the instruction manual, that he knows or gets some information what is the working principle of this IRF and what are the consequences. So for example, on the water hardness, the consumer for sure should know how much additional water is needed when he is living in a soft water area or when he is living in a hard water area, because this additional amount of water can be, let's say, much higher as what is saved by the water softener. Yeah. So we want to see, to verify if the information as given by the manufacturer is correct. And we want to have the possibility, the option, to measure and to verify if these additional consumptions of the IRFs are correct. Yeah. So we need also to have a methodology how we can really identify the consumptions in the different IRFs. So at the end, we want to be able that we can inform your client when you are a laboratory or the consumer, saying, okay, here is the basic consumption, but be aware that when you are using this product under these and these conditions, you are consuming so much more energy or water or time. And this is what I think we need to have as a minimum, the individual values. And then we, or let's say some regulatory body, can also take those values to calculate something like an average mean or weighted mean, to say, okay, the realistic consumption for this product under this water hardness condition is 55 liters. Also, the machine is declared with 45 liters. Under those conditions, it will consume 55 liters or things like that. Yeah. So it's not on us to say how these calculations have to be done, but we are delivering the basic values which are needed to calculate these weighted mean. Because for this, you always need to have some assumption on what is the usage profile of the machine. So are there 7 washes done per week? That's even not sufficient. If the 7 washes are done day by day, then you would never come to the point where the tank has to be emptied. But if you do the 7 washes just on Sunday, and that the machine is staying for the rest of the week, then you will come to the point for sure that the tank will be emptied at least after the 7 washes. So there is some assumptions needed on the usage profile to be able to calculate this average consumption. So to follow this principle, we need to have this point 2a, or it's beneficial to have this point 2a, that the manufacturer is informing in the instruction manual on the function of the IRF, including what additional consumptions may come out of this IRF at certain use cases or at certain conditions. If we are not able to get this information by the manufacturer, or if we are not able to measure the IRFs by doing a high number of cycles to identify the function of the different IRFs, then we only can say, sorry, we gave you the option to clarify what this unstable behavior of your machine is about. But if we can't verify it, then we only can take those values which have been measured, let's say, in a series of 5 runs. So yes, this is what I said a minute ago. If we cannot get the information from the manufacturer, or if this is not correct, we should measure by ourselves those intermittently recurring functions. And to do this, we also have given you, let's say, some procedure how this is done. And this depends also on the required statistics. So meaning how many number of repetitions of the same cycle you want to have before calculating the standard deviation. So normally we take 5, or we can take 3. So we have to define what is this number which we want to have. And by doing this, we then can go and measure the machine and see how long it takes to come up with the minimum number of each of the IRFs to happen. So the procedure would then be that we are measuring test runs in this test machine up to we reached this minimum number of test runs where this IRF is triggered. And this is why it is called trigger cycle. So this is where the IRF is, yes, triggered by the logic of the program, where this says now you have to happen. So you have to rinse the or regenerate the softener or whatever it is. Yeah. So this means we may have to make many runs until we get a sufficient number of those trigger cycles. And then we can say, okay, now we have, let's say, 3 of those specific cycles where the IRF is triggered. And now we can calculate what is the value of these cycles. But as a consequence of this, we may need to run many runs to get this required number of trigger cycles to happen. So think about the water softener example. If the water softener asks for a regeneration all 10 cycles, then to get this trigger cycle, you may need to run the washing machine for 30 cycles. Yeah. So just to have 3 of those cycles where the water softener is flashed in your test series, which means it can take quite a long time, and for sure it will also be very costly. So for this case, we have introduced an allowance in this standard to, let's say, make these tests a bit less costly. And this means that when you are able to anticipate when is the next trigger cycle to come, then you can run the cycles which are in between, which are called here preparatory cycles. Then you can run those cycles under, let's say, simpler conditions, so that you don't need to have the efforts, especially the efforts of putting in test strips, which you anyhow would not analyze at the end, but it would just add cost. So For this, we have introduced the possibility to use ballast soils for these preparatory cycles. Yeah? So this gives you some allowance to make these preparatory cycles cheaper. So let's make a look at this example of this regeneration after each 10th cycle. So when you know that, then you start your first 5 test cycles are used for the basic consumption, and then if you know, then the 6th to the 9th cycle would be just preparatory cycles. So here you could exchange the test strips by ballast soil, and then the 10th cycle you would measure again with test strips. From the 11th to the 19th cycle, you would again run this preparatory cycle. The 20th would then be a trigger cycle where this regeneration happens. And from the 21st to 29th, it would be again preparatory cycle. So this is how this would work. And this is described in the standard. Yeah, it looks a bit confusing, but having understood what is the concept behind, that we want to have the right number of cycles with this IRF, and we also want to be able to test various IRFs together. So machines may have, let's say, 2 or 3 IRFs in their program. There is some general description how this can be done and should be followed. So don't be confused too much about this diagram. So this is a way how we can verify the basic consumption and the additional consumption coming by each IRF. But we don't want to follow this route always. We want to ask the manufacturer to provide to the consumer a correct information of how much additional consumption is caused by this IRF. And this is what is the intention, because we, in this step 2a, we then only go to verify if this information given by the manufacturer is correct. We don't, let's say, normally then go and verify if the consumption is 100% correct, but we just show or look if the consumption is obviously correct. And this is what we are asking for also in the NXT, that the consumer is informed about the IRFs and what they are doing and how they are triggered. So if it's water hardness elimination, one can say, okay, it depends about the water consumption, and it depends about the hardness. And you should also inform about the additional consumption coming by that. So here, for example, in this example, regeneration uses 5.4 liters and costs 12 minutes in program duration and almost nothing in energy. So this kind of information we want to see in the instruction manuals, so that we can verify in our test if this information is correct within tolerances. And if it is correct, we don't go normally on testing 20, 30 different cycles, because nobody could afford all these tests. But we can do these tests if we want so, but it's probably not the usual way. I have looked already on some instruction manuals, and I found some information already there. For example, on this tank storage duration, So here you see there is a factory setting of 36 hours, but also other possibilities. So the consumer can decide which setting he is using. And it's described what is happening and how much is doing. What I not like to see is what is written in the bottom of this box here, that this tank storage emptying, that this is set to off mode only in the case of the eco program. Not emptied after a power failure. So this clearly is some hint for circumvention, that here the manufacturer wants to be measured always with the lowest energy and water consumption. And this is not a realistic information to the consumer, as the manufacturer describes that the tank storage should be and could be emptied after a certain time. The same problem is on the right side, where it's coming about water softener. Sorry, I only have a German version here. Here it is described that there is additional consumption, quite clear, but the information is only valid for the eco program at a water hardness of 13 degrees German hardness, which is not the right information we want to see, because let's say the program, it's a standard, is suitable for testing all kinds of programs, and we don't want to have only eco programs to be tested. So there is room for improvement to get this done better, but the basic is available, which is the measurability of those IRFs. So what I just want to show to you at the end of my presentation is how do I come to those values here? Wow, where is it? Oh yeah, at the bottom it's written. So what I assume for these data is I have a water softening which is flushed every third cycle with 5 liters. And I have a water tank in, which is emptied with 20 liters every 5th cycle. And then depending on where you start, you can come up with this very different consumption values as you have seen in this example. So yes, now I am open for questions, please. Please, questions. This is quite new, so you should have many questions. But they aren't. Okay. Then I thank you very much. And I now hand over to Rene, which will tell you what was something about another new annex in the 6th edition. Rene, are you available?
Yes, I am available. Thank you, Rainer.
I have stopped my presentation.
So I can share my screen.
Yes.
Let me see here to share. Okay.
Now something comes.
Very good presentation.
It's starting.
Okay. So please let me know if you see my screen. I hope the network is not too slow.
Now we see something. Yes, we see your presentation.
Good. So, good morning, afternoon, evening, everybody. Rainer, thank you very much for the opportunity to elaborate on the multi-compartment washing machine today. I'm glad to contribute a bit to the IAC world in this way. Let me introduce myself. I think I'm famous like Rainer. I'm working for laundry industry quite some time, 15 years, a bit more than that. I'm working as well for standardization in IAC, Senelec, German standardization groups for more than 10 years. And currently I'm working as a senior chief engineer in Midea Little Swan in Wuxi, China. Should be enough from me. Today we're going to speak about the multi-compartment washing machine. So we try to understand what makes it multi-compartment washing machine, how to prepare this machine, what to measure, how to measure, and then finally how to evaluate the data and how to report the data. And we're going to start with the definition of the multi-compartment washing machine. Here you can see some examples of a multi-compartment washing machine. So basically it's every machine with more than one drum. It doesn't actually matter, it's in one casing or in separate housings. So you can see the examples here. Can be two machines stacked together, can be two drums in one cabinet, can be as well a kind of pedestal washing machine, but can be as well two separate machines connected and sharing some means. So the definition of the machine is clear, but how to measure? The most important thing here is to measure the multi-drum mode. It means to measure the machine when it's doing something in several drums at the same time and not doing the one drum alone, which would mean we can stick to the measurements we know already to evaluate the machine as a single drum machine. So what we are looking at today is the simultaneous program. Means it's a program which is running 2, 3, however how many drums simultaneous and working together to wash the certain types of textiles at the different drums in the same time. So we should start with some basic rules, let's say guidelines. If we do the measurement in this simultaneous program in the multi-drum mode, what we want to know? We want to know for sure as much as possible what each separate drum can do. So if this machine can be operated separately, every drum in the selected program, we would do so because we can evaluate every drum completely separately. If we use the multi-drum mode on other programs which are not simultaneous, for sure we can measure like this. We are back to the standard procedure and can measure every drum separately. Only in the case we are running the multi-compartment machine in this simultaneous program, so in the multi-drum mode, that's the one we are doing some of the measurements combined together. So how to do this test is the next step to discuss. So the first thing we need to understand is the rated capacity. And you can see there is different options. So it might be there is no declaration from the manufacturer about the rated capacity. No declaration for the single drums, no declaration for the combined capacity. In this case, we're gonna evaluate the capacity based on the NXN. So same procedure we do as well for the normal single drum machine. and we calculate the rated capacity for each drum separately. A second option would be that the combined rated capacity is declared, but there is no split for the single drum. In this case, we can still measure the drum volume, and we can build a ratio and give the share of the rated capacity to each drum according to the volume ratio. In this time, one specialty applies. For the calculation of the detergent amount, we define that in this case, only one time we apply the fixed part of detergent. So we would calculate the detergent amount based on the rated capacity once, and then give as well the same ratio of this detergent to each drum based on the volume. And then the third, and for sure the best way, is that the rated capacity is fully declared by the manufacturer. So each drum has a declared rated capacity. This is the for sure preferable way for the testing laboratories. In this case, the rated capacity is clear and the detergent amount is calculated accordingly in accordance with this rated capacity. Then we go for the test preparation, and you can see there's not much new things I can talk about. So the preparation of the test machine before doing the test, same as before, no difference. Everybody know how to do it. The test load per drum, how to prepare, exactly the same as today for the single machine. The important part here is that a dedicated test load should be assigned to each drum. So within a test series, you should make sure not to exchange the loads. So in case you have two drums with the same rated capacity, do not switch the loads in between the test series. And for sure, as usual, not to exchange or mix some items from the test load. The test materials and the loading of the machine, the loading sequence, same as the single machine. So should be no problem to execute this preparation step. So here we can see on this slide the test execution. You can see we start from the top with the preparation of the test load. We prepare the machine, do the conditioning, put the test materials, the monitors on the test load. We load and put the detergent to the chamber. We select the simultaneous program and start the measurement. So now all our drums should start working, but they may not work all at the same time. So some drums may finish earlier, some drums may finish later. So here is important to regard that each drum, after it is finished, within the 10 minutes time frame, you should unload and remove the tracer textile. So step by step, drum by drum, we are going towards the finish of the simultaneous cycle until all the drums are finished. And once all the drums are finished, we can stop the overall measurement and record the combined parameters. So now about the data recording and evaluation. As I already explained in the beginning, we want to know as much as possible details for each separate drum. So wherever possible, we will evaluate and record the data for the single drum, only in case we cannot distinguish different drums in the measurement. We have to live with the combined measurement. So in our example, the cleaning performance, for sure, we have an assigned test load per drum. We have the test strips per drum, so we can evaluate the results per drum. Same for the water extraction performance, rinse performance, cold water cleaning performance, wool cleaning performance, and the gentleness of action. What we cannot do for a simultaneous cycle, we have several drums running, and as shown on the last slide, our program time is the time when the last drum stops. So what we record here is the combined program time for the overall machine from the start of the program to the end of the program. Same thing for the energy consumption. We cannot distinguish different drums' energy intake. And as well, for the water intake, we cannot measure with the normal effort the water intake per drum. So here we take the combined value for the overall machine. Last thing after we got all the measurements is the data reporting. And here on this slide, you can see on the left side the template from the IEC standard for the single drum machine. And you can see there's quite plenty of data which are unique for the machine, but not unique for the drum within the machine. So due to this reason, the suggestion here was to split this template into two templates. So we would have a template which is recording or documenting the overall machine parameter, which are same for each drum. And then we would have n times templates for the individual drum to record the measurements for this individual drum's value. In this way, we avoid the duplication of data. So we avoid typos, we avoid redundant data, and we keep it as much as possible streamlined. And that's already the end. So any questions? No questions? Then I think you saw this already a couple of times about the availability of the data for these webinars. If there's no questions, I give back to Rainer or immediately to Gundula.
As far as I can see, Rene, there is a question on the chat. It says,
okay,
hello to be Do you see it?
I need to change. I'm still in the presentation mode.
Yeah.
But yes, I can have a look. I would say not necessarily need to have the same power cord even. They should share something at least. If they don't share anything, they're completely independent. So it's like two machines running at the same time independently. But it's, in my opinion, not necessarily the same power cord. You're welcome. Any other questions?
Thanks a lot, Rene, and I hope to see you soon again in good old Germany.
Yes, latest in March. I'm going to be back for some time.
Good. So then we go on, and the third part are the low power modes, and here Gundula will tell us something.
Thank you, Rainer, for the introduction. I will share my screen, and I would like to give you a short overview about low power modes. This is the third part of our today's webinar. And from the agenda point itself, it's mainly about NXL. but I will also, as done before, focus a bit on what used to be there in edition 5, as well share with you a couple of insights, because what we see in CD2 right now on the low power modes is to some extent copy and paste from Europe. Low power modes in the discussion of SC59D working groups do have a long history. It started many years ago when with edition 5 the first part of low power modes were introduced. So in edition 6 CD2, and this overview you have seen today already, we have the here mentioned low power modes considered in Annex L. That does not mean that off mode, standby mode, networked standby, delay start, and left on mode are the only low power modes. But these are the ones that we now gonna consider in the 6th edition of IEC 6456. So I copied into the presentation of today the definitions from CD2. And I would like to mention here that on this first slide, you see those definitions that were copied from the latest version of the European standard. So you see the off mode, which is well known for many years and easy to identify. You see a definition of standby mode, which is, I would guess, known to others as well, because there's also separate standards that looks into all household appliances and even other equipment. About standby, there was a lot of discussions, and there's a separate standard that you would like to consult on this topic as well. Then for washing machines, delay start is a quite common mode nowadays. So therefore, this is included in CD2 now as well. And networked standby, or the connection to network, and that's the definition in CD2. What means network is quite common nowadays as well. Not saying that all washing machines are connected to the network, but some of them today are able to be connected. So therefore, we need to take into consideration this connected mode as well. Wrinkle guard function is a new entry into the standard here, but we discussed this already a couple of years ago. Well known from dryers, but sometimes also relevant on washing machines to avoid sitting in wrinkles after the end of the cycle. This is also in other standards considered, and it's a common, well-known function. So therefore, we have included here a definition now as well, because at the end of the cycle, this may last for quite some time before it is interrupted. The other definitions, there the source is actually the European standard from 2016. And the definitions now taken over from the European standard from 2016 started off with edition 5, where off mode and left on mode was already defined, but we are specifying a bit further the principles how to measure especially the left on mode. You see here in these definitions a couple of modes that can happen after the end of a program, because it was not the case that all washing machines automatically switch off. So therefore, some of them remain on forever if you as a user don't switch it off. This was considered in Europe, and therefore the measurement after the end of a program was divided into two post-program phases that you see here on the screen. One is as long as the machine is still switched on, for instance, showing on the display certain status informations. And the other one is after the program was switched off automatically or not automatically. The automatically switching off is linked to a terminology. This is called power management system here in this case, and therefore this definition was included here as well. We will come back to the elements of that further. So then on the next slide from Annex L, there is one essential hint. There is included in Annex L a table L1 that gives you clear instruction in which sequence you can test all the modes that were explained in the first part of the definitions, copied from the European standard of 2020. This table L1 considers that the washing machine should switch off automatically to off mode or standby mode after 15 minutes. But for sure, this is not necessary everywhere, even though in Europe it is now stipulated. If this is not the case, then the washing machine shall be switched off manually in accordance with the manufacturer's instructions. So this you need to keep in mind when you follow the sequence in table L1. And there's a couple of side elements that need to be checked. So the machines should always stay connected to the main power for the duration of the test. There should be no warnings, no error indications or things like that. This laboratory supply water is left on at the specified pressure as we have it in our standard. And when it comes to network connectivity, for sure you have to follow the instructions of the manufacturers. This, by the way, was the topic that caused most of the issues in a recent European round-robin test. I don't know for this round-robin test if there will be machines with network connectivity and if they are to be measured in this round-robin test. But in case that happens, that you have to test in your laboratory the network, the connected mode, then you need to follow the manufacturer's instructions because this is essential to make sure that it really works. It might be also an issue that not all washing machine laboratories of today are equipped with network connectivity in their rooms. So therefore, we also realized during the European round-robin test that sometimes these specific modes are measured in a different laboratory. And also for this, CD2 takes into account that it must not be the washing lab itself where you measure the low power mode. This just as a hint to the participants of this round-robin test in case you have to measure a network connected machine or in your future work. One key point that I would like to highlight here, the last dash in this list reads no user invention on the washing machine besides unloading. I'm aware that there are differences in different regions of the world because it is a question how you measure the machine after the program was finished. In Europe, and that's what we also have here in our definitions, especially in table L1 included, it is supposed if the washing program is finished that you open the door. If I'm not mistaken, but this needs to be clarified then also by other regions in their local standard, in the Australian standard, it still reads the door or the lid remains closed after the end of cycle when measuring the low power modes. So therefore, keep that in mind and check that. In IEC, it is now clearly the case that the left on mode is measured after the door was opened. Let's go into the table in Annex L. It's the table L1. And this is the first part of this table. And this is about the measurement of standby and off. And in all cases, this measurement should be done over a period not less than 10 minutes. So keep these 10 minutes in mind when doing a measurement, but make sure to measure the time and also the electrical power in that period. But what are the steps in this table and why there are so many columns? The 4 columns of this table aim to differentiate between different types of machines. So the first column is a machine that has no delay start and is also not able to be connected. So therefore, this is a quite simple machine. And in the first column, you see the steps that you have to do to measure the off mode or the standby mode of such a machine. In the second one, we include already the delay start. I mentioned nowadays this is quite common. And the two other columns are related to machines that can be connected either with or without delay start. And in any case, first you have to connect the machine to the power supply. And remember, you wait for 15 minutes, and then the machine could be in off mode or in standby mode and can be measured. Then the second step is to switch on the appliance if it not was switched on. And then you may, because it's optional, program any run. That means it can be any program from the program dial, and you program that. And then after another appliance interaction, and here we have a note, and we will come back to what is appliance interactions, because this is also discussed quite a lot in the application and the round robin test. Then you wait another 15 minutes, and then you measure the electric power again. So in both these cases, you may come up then with the measurement of off mode or standby mode, and that depends on the machine itself, how it reacts. About these appliance interactions. This is now a copy from the European standard, and we may further need to improve also the language in CD2. This is why I put this one here, because we had a lot of discussion about that. And relevant appliance interactions for the measurements is the switch on of a machine or the switch off whatsoever. At the end of the program, there can be any further activities, and you might need to interrupt the wrinkle guard function, because this would be also an appliance interaction. And then again, a bit more refined, any interaction, clearly stating it can be either directly, that means physical, that means I touch the machine, I turn the knob, or I push a button, or indirectly, for instance, via remote user interface. In case of connected machines, that might become a typical interaction with the machine as well. And you have to keep in mind, no other mode, including emergency measures, should be triggered when doing the measurement. Remember, we had that a couple of slides before. With that, I would like to go back to the table L1. And the next one to discuss is network. For sure, only the two last columns are filled in here. And it starts with turning on the appliances if it is not already turned on. And again, optional, you can program run. And for sure, you have to make sure to activate network standby. You wait 15 minutes, and then you measure again the electric power, and it should be the so-called network standby that you measure in this case. And after that, you would turn off the machine in the further sequence. And again, this mode should be measured for not less than 10 minutes. Next point would be the delay start. So switch on the appliance, that's normal. If I would like to program a delay start, I can select any program. In case of connected machines, I have to activate network connection. And then you should activate a delay start for a minimum duration of 30 minutes. It can be any longer time, no matter, because after that you wait another 15 minutes and then you measure the electric power for a minimum of 10 minutes. So therefore, the minimum duration for active delay, that's easy to understand, should be 30 minutes. Next point is left on, and now we are switching back to what used to be there in Europe and what was discussed a lot also in edition 5 for IEC 6456. And the decision for a practical measurement is now copied back into this table. In Europe, this is not measured anymore, but it might be other regions of the world that still would like to use this kind of measurement after the end of a cycle. So you switch on the appliance, you program any run, and at the end of the run, means the machine should really do a program. you open the door, because that would be normal behavior in the household. You would like to unload. And then the electric power is measured in the so-called left on mode unstable for about 30 minutes, taking into account that maybe during this period of time already the machine automatically goes to off mode, but the measurement should last for 30 minutes. After that, you would switch off the machine or not switch off the machine, depending on the instructions and depending on the concrete measurements you would like to do. In Europe, we did not switch off the machine. We were measuring for another 10 minutes the electric power and considered this the left on mode stable. So the idea behind this concept was, let's wait for 30 minutes because then all information displays and so on could be switched off. And then you measure the left on mode that lasts forever if you don't switch off manually the machine. This is the picture also coming as a source from the European standard from 2016 that visualizes the specific measurement at the end of the cycle. So after the end of the program, you open the door, you adjust your measurement devices, and here a clear hint, these electricity consumption that we measure here is very, very small. So therefore, you need good equipment with a good resolution and possibility really to measure such low power modes. There is other IECs referred to in Annex L, for instance, IEC 62301. This is quality requirements for the energy measurement, and you would need to consult that to find appropriate equipment for the measurement of these small energy consumption modes. And you have another IEC that you may want to consult in case of network appliances. This is IEC 63474 about network standby. Those standards will give you further hints what you need to consider to have the appropriate equipment for such measurements. The electric power of the specific mode is calculated from the measured data. So you measure the energy consumption, you have a certain measurement duration. Remember, it should be more than 10 minutes or about 10 minutes, but not less. And you calculate for any of the modes that we have discussed so far, according to this formula, the electric power that was measured for one specific low power mode. We have a new table in Annex S. This is the table S19. I did not copy it here because it always gives you, for each of the modes, the same details. You should report the energy consumption for that mode, you should report the duration of that mode, and you should calculate the electric power measured. This is the overview that I mentioned before. So in edition 5, we had off mode and left on mode specified already in an annex. In Europe, we went one step further. We took over the off mode, but we differentiated the left on modes in a stable and unstable period, as mentioned before and shown also in the picture. In the European standard from 2020, we have now off mode, standby mode, delay, and network. And in the IEC edition 6, we will put together what was done so far, having off mode, standby mode, delay start, network, and also these two left on modes that were measured in the past in Europe. The Australian standard, and here I'm not sure, but I believe we have some Australians with us here today. From their standard, I know there's the off mode because this is where the international standard edition 5 was coming from. And I know that there's an end of cycle mode and a post-program mode, and all of this is measured. And the difference, the only one I'm aware of, is the point of the open or not open door. I'm not aware of any other standards around the globe that you may want to compare to this set of low power modes. Nevertheless, if there is update required of this table, let me know. I can easily do that before sharing it with the community. With that, I'm at the end of my talk today. Are there any questions regarding the measurement of low power modes?
So the floor is open. Please. Oh, I see. There is not a lot of discussion happening here in these webinars. So you don't want to challenge us with your questions. So I have to thank Gundula once again for her contribution. So there is time to ask questions.
So thanks a lot for listening. And if there's later on questions on lower power modes, feel free to contact me at any point in time. If I can help, I'm happy to do so.
Yes, I think this is true for all our presenters which we had here. You have now got a good introduction to the specialities of many people. And I think I'm quite sure everybody is willing to help you if you have questions. So you can contact each of us or contact me and I will forward it if I can't answer. So this is then the end of the webinar series which we planned. Also, you don't like to ask questions. I would like now to hear a little bit of feedback from you, how you found this webinar series. Was it helpful for your work, or what could have been improved, or what could have been made better? Please, don't be shy. You can open your microphone. Please, some feedback.
It's Phil Robinson. Perhaps I could speak for Peter in Australia. He told me he found it very helpful and very good.
Thanks a lot. Louise, you opened your microphone.
Yeah, it's the same for me. The webinars were very helpful. For sure, I will watch it many times to be sure I can catch all the points. Thank you very much.
Yeah, you're welcome.
Louise Christmann speaking. I followed not many of these webinars, but I have already saved the YouTube link for checking the ones I missed. Thank you very much. It was a very good idea. Yeah,
this is a good point. YouTube, so 9 of the webinars are already available at this YouTube channel. And the 10th, this webinar of today will be available tomorrow, I would say, at latest. More comments, please. I see from comment from Elisa on the chat. Thank you. Christine, thank you. Stephanie, all good comments, my God. Yeah, so then we have to apply all of that, what we learned in the round robin test. I wish you good work in the round robin test. Whenever you have to do it, maybe in half a year time when you do the tests or earlier. Now you'll know where you can look up something and where you can find some explanations. Use this possibility of the YouTube recording also to teach your colleagues which are working on those tests so that they also can learn something. And yeah, thank you very much for participating. We had a good, very constant participation to these webinars. Many, many thanks to all the presenters, which were really putting a lot of efforts into to make all the topics presentable, and they all made a good job, a very good job to bring over the content. And I thank them very, very much for their efforts. Yeah, then this brings me to the end. Thank you very much once again. And I hope to see you somewhere in the future. And I wish you good success and best health.
Yeah, and
conditions.
Rainer, many thanks to you for putting all together here and holding the strings.
Yeah, it was not so much. I could only organize it, but you were doing the jobs. Thank you very much. Okay, and bye. Bye-bye.
Thank you.
Bye.
Bye-bye.
Bye-bye. Thank you.
Thank you very much.
everybody.
Bye.
Thank you. Goodbye. Bye bye. Thank you.